Now this phi I is here, I have rho I here. Let us first do one by one. Okay, now what is rho I? Rho I is basically charge density, right? Now how do you calculate charge density? Basically you have to take the density of ions, okay, because charge density is connected to basically material density, and then how the ions are carrying charges. As simple as that, right? Now when you measure something means suppose a concentration, okay. So what we are saying, remember this charge density rho I is around a particular cation. Okay, say due to a cation, what will be the charge density? Clear? But that is slightly different, okay, from your actually numbered density. Meaning, what I am trying to say is that suppose there is ion, okay, and there is a species, and there is suppose no like attraction between the other species, okay, no attractive force, just a very ideal system. Then the density around it will be same everywhere. It will be identical to your bulk density. Moment you are talking about charges, the density will be influenced. Clear? Because cations will basically try to evaporate around anions and vice versa, right? Which means actually, but what do you measure when you add to solution? You always measure the bulk density. Okay, because you know that what is the amount of mole and what is the amount of this thing. Okay. So what I'm saying here is that the density will somehow be different. Now how do you calculate it? How do you calculate the densities are different? Meaning what I'm saying here, I have some charge here, okay, and due to this charge, I'm asking what is the density of molecules or the ions here. Okay. So that will be slightly different from the bulk densities. But this difference in population, you can always go back and think in terms of Boltzmann distribution. How? Because I know that if there is some stabilization, okay, compared with the bulk densities, okay, I'll have some preferential accumulation. Okay, just as simple as that. Now, what is this energetic thing is coming from? It is because of this potential. There is, if I put a charge here, the charge will gain an extra energy due to this potential. That will create an energy difference. Okay, and that will be basically controlled as a Boltzmann distribution. So what I'm saying mathematically is, I have a charge density which I'm writing as C. Okay. Not charge density, sorry. This is basically the number density, okay, of say species I, okay, species J, whatever, okay. And then I have, let me just call it as a J, okay, in the sense that this was I, okay, and this is suppose J. I and J can be equal, meaning it is cation, it can be cation, anion. If it is cation, you can think that there is a repulsion, right? So the density here will be less than the bulk density. However, if it is a cation anion, the density here should be more than the bulk density. That is the simple concept. Okay. J can be cation anion, I also can be cation anion. Okay. Now what I am conjecturing here, this thing, Cj, which is basically the concentration of the species J, okay, at some distance from that central thing, which has a species I, okay, this ratio, meaning which is the bulk ratio, will be proportional to the Boltzmann factor. Okay, and what is Boltzmann factor? It is basically e to the power minus some energy by kBT, right? Now what is this energy? This energy is having because I put a charge J at some distance, okay, from the central ion which is I, but the distance I don't need to know because I already know due to this charge, the potential created is phi. Clear? Okay. So if there is a potential created phi I, okay, and what is the charge on the Z? Sorry, on the J. Charge is basically like, it will be Zj, suppose. The same notation I am using. Zi was for I, Zj is for J. Okay. I have to always multiply it by the fundamental charge. This is basically Q. Okay. Times the potential. Potential due to I. This is the energy. Okay. If I divide it by kBT, then I will get the Boltzmann factor. Okay. This can be repulsive again. Okay. If the charges are of similar type. Okay. Or can be attractive. Clear? That is hiding what is the sign of relative sign of this phi and j, right? So this thing, okay, will control the ratio. Clear? Now, actually, I do not need the number density. I actually need the charge density. But I can always write the number density first and then rewrite the charge density. How? Because I know what is the number density of charge density around this cation rho I. Okay. So this is basically the density of the cations and density of the anions together. Meaning I am writing it as something like around it. Okay. So I'll just write it around it. Basically, some cations and anions are accumulated. Okay. Now, what is the concentration of cation? Like I am writing it as C plus. Okay. What is the what is the charge of the cation, which is Z plus? Okay. And then remember, this is actually these densities we are writing in terms of molality. Or for 1 mole. Okay. In a sense, like I can actually write what is the total charge here. C plus. Let me just I think we can have an alternative definition. Just a minute. So what I am writing is basically the charge density. Okay. Charge density is basically number density multiplied by charge. As simple as that. Okay. Now this charge density for a kind of molar thing. Okay. For cations, I have Z plus cation. Each cation is giving you how much charge? Let's say Z plus into E. Right? It is minus E basically. But then for 1 mole, I have to again multiply by E times Avogadro number. Clear? That I can directly replace by F. That's the fundamental definition of this charge, Faraday, right? 96,500 coulomb order. Okay. Similarly for the anions also, I can write it as C minus Z minus into F. Clear? Okay. Now, here we one thing. So, these things, C plus and C minus, I do not know. But I can always use this equation. I always know what is the cation's overall density and the anion's overall density, number density. Okay. Suppose I gave you sodium chloride. You dissolved it into some water. What do you know? How many number of sodium atoms or sodium ions are there per unit volume, right? But that is drastically modified in presence of the other chloride ions or other sodium ions. That is the thing. How it is modified? Because of this relation. All I know is Cj0, something, those things. Okay. What I am saying here is that this C plus is nothing but C plus 0 times the Boltzmann factor. Okay. Which is nothing but e to the power minus. I am talking about now J is being plus. So I will write it as Z plus E phi I by kBT. Clear? Into there was an F. Clear? And then I have C minus. Similarly, I can write the C minus also the same way. C minus 0. Okay. Times e to the power minus Z minus E phi I divided by kBT. Clear? So this is the charge density. Clear? So how do you get the charge density? Charge density is basically the number density multiplied by the charges. Okay, for each atom. But that thing I cannot measure actually, C plus or C minus, because that will be modified, right? But I know always, okay, that has a connection with the bulk density which I have, because I know how much amount of the ions is dissolved. Okay, for the cations, for the anions. For example, if I need sodium sulfate Na2SO4, the concentration of the bulk concentration of the cations will be twice than the anions. Clear? Okay. But I only know the bulk concentration, but that charge density is not connected by the bulk concentration. It is connected by the local concentration. Okay. How local concentration is defined? That is basically the local potential, how it is changing. Clear? Due to the central ion I. Now I is interacting with I, same, like cation is interacting with cation is interacting with anion. All these things we have to consider. Clear? Now then I got a basically expression for the charge density. Okay. Now this is still not a very bad expression in the sense that it has e to the power I, phi, all these things. Okay. Now the thing is that what I have is cavity, and this first thing you do is basically expand the exponential, and do not consider the higher order terms. Okay, e to the power x, I can write it as 1 plus x. In this case, it is e to the power minus x. So I just take 1 minus x. Okay, and see what is happening. Let us just do it. I have basically c plus 0. There is an f here. Okay, yeah, in question.
So we have z plus z minus
Which one?
in the second step.
Here. Okay.
It will multiply to z plus.
Oh, sorry, there is z plus also. Yeah, there is a z plus, there is z minus also. Right? Yeah, so I have c0 plus z plus f. Okay. Into, let us expand this thing. Expand, if I do it, it will be 1 minus x, right? X is what? Z plus e phi I divided by kbt. Okay, I'll have a similar term for the minus. Okay, let us just do it. So I'll have c, can you see it? Okay. I'll have c minus 0, z minus f, 1 minus, all the classes will be replaced by minus. Okay. By kbt. Clear? Okay. Looks very complicated. Okay, let us see where it is going. Alright, so let me just write it. This term and this term, let us first write here. Oh, what is that thing? C plus 0. Oh, Z plus, there was E. Sorry, not E. E and A already got cancelled. Okay, and then I have C minus 0, Z minus A. This is basically addition of this term and that term, one terms. Okay, what is this? What is C plus 0? C plus 0 is the bulk concentration of the cations. Okay, you can think how many numbers are there per unit volume. Okay, Z plus is the charge. F is common, right? C plus 0 into Z plus and C, addition with C minus 0 into Z minus has to be 0 because the entire thing is electrically neutral. Right? Sodium sulfate. Charge is plus 1, amount is twice than the sulfate. The sulfate charge is minus 2, amount is just half. If you just add it, these first two terms have to be 0. Clear? Okay. Then I'll be left with only the last two terms. Last term is second term and the fourth term. Okay, first and third addition is 0 because of electrical neutrality of the entire thing. Okay, again it's the entire thing because actually it's the bulk concentration, which makes sense. C plus and Z plus locally may not cancel each other with C minus and Z minus. Okay, there can be an excess step. That is the meaning of this ionic atmosphere. Clear? Okay, but in a bulk sense, of course, they should always cancel each other. This is basically concentration times the charge of cation. Concentration times the anion charge has to cancel. Clear? Okay. So the first two terms got cancelled. So what I will be left with is plus. This is 0 for electrical neutrality. Okay. And what I'll be having is basically, let us see. I'll have. Let us look at here. I have C plus. I have Z plus. Z plus will come twice. So I'll have basically ZI square kind of thing, right? So I'll have here Ci, or let me just write it as a plus. The first term got cancelled. Then I'll have C plus 0. Okay. Between these two terms, okay, what is the difference? C plus, Z plus, these are the different terms. F and other things are common. Okay. So I'll have C, this thing, C minus 0, Z minus square. Okay. What are the other things? I have one F here, E phi I by kbt. Clear? F E phi I by kbt. Clear? Okay. Now, the thing is that this I can also modify, like at this stage, in the sense that what is E? I can write it like this. Okay. So then this factor will be, if I just replace E by F by Na, this will be F square. Okay, phi I. Na into Kb will be R. Okay. So I'll just have F square phi I RT. Okay. Now look at this term. Okay, what we are going to prove is basically the ionic strength. Okay. Now ionic strength, what was the definition? Remember, it was basically what? I. Tell me what is the definition? Half. You just wrote it, right? There was a summation, right? But in the summation, if you remember, there was basically molality, right? But this is basically bulk concentration means is molarity. Okay. Now we have to make another approximation. In the sense that this molality and molarity, there is not much difference. Okay. So if you make that approximation, okay. So what I am saying here is that we can actually write it as something like, again, this is an approximation. Okay. This term, we'll write it as something like B plus, okay, for the bulk molarity, okay, Z plus square plus B minus Z minus square, okay, into, basically I have to multiply by the solvent concentration. What do you mean by this? So what is molality? Anybody? Definition, molality. So this is basically number of moles of solute per gram of the solvent, right? When you define molarity, it was basically number of moles per liter, right? So there should be a connection between solvents amount to solvents liter. That is basically the solvents molarity. That will automatically come. Just from molarity to molarity, when I convert, I have to actually write also, like, say 1 kg of water means how much in terms of the volume, right? That's why this concentration of water is coming. Clear? Okay, that's a dimensional thing. Okay. And then I'll have basically all these other things, which is F square phi I by RT. This already I defined as ionic strength, but there was a half factor. Okay, so this will be nothing but twice the ionic strength. But remember, in the ionic strength definition, I was writing Zi square B plus, and there was divided by B0. That was basically the dimensionless thing, just the unit. Okay, so what I'll be having here is this rho I, okay, which is the charge density, okay, for the ice species, okay, which is equal to twice I, okay. I should have a B0 because if I divide by B0, then only get an I, and then I'm multiplying by 2, dividing by half, multiplying by half. That half, this B0 thing was the ionic strength, right? That's why I'm multiplying by 2 and B0, and then the rest is ionic strength times I have the solvent concentration F square phi I by RT. Fine. I'm basically reducing the problem. Okay. All right. So what I got is basically rho I is this. Okay. And then what is the rho I? Yeah. Then what will be my RD? Okay. That's a straightforward thing. So I have basically rho I here. Okay. That is the rho I thing. Okay. So this is RD square. Clear? Okay. So what I'll be having is just one. In the rho I definition, if you remember that we took a sum, right? It was 1 minus x. There will be a minus sign here because I was taking the summation of this thing. Okay, so there will be a minus sign here, minus sign here, minus sign here. That minus will give you a plus basically. And now I have a definition for RD. So RD you can just add in, it will be epsilon RT divided by twice rho. Rho is the charge density. Twice C theta F squared on BZ. Whatever. Like I have some thing. Okay. Now look at it. Now this divided. Okay. After I replace the rho I. Okay. Has a very interesting description. The reason is there was a phi I here. The phi I is got cancelled. And then everything you can calculate. You know the permittivity. It's a bulk thing. It's a R, it's a T, 2, concentration of the solvent, okay, Faraday constant, ionic strength, which you can calculate, and the unit of molarity. Okay, fantastic. Now actually I can calculate the potential because I know what is RT. Clear? From everything which you know. Okay, fine. RT is known, but at the very beginning, what I said is that I have to calculate what? I have to calculate the work done. It was basically ln gamma plus minus was the work done divided by this thing. Okay. Now that is the only part left. Okay. How to calculate the work done? Okay. If I can do it, I can get basically all the divide calculator. Okay. Everybody is following up to this point, right? Okay. All right. But now you can read Atkins and you will realize, okay, because there are like many things here. Okay. Now just go a step back and just think. Okay. So basically, what I am saying here is that I have to just calculate that now the activity coefficient. Okay. And the activity coefficient already I wrote that this is the work done was equal to the mu's, addition of mu's, right? At the very beginning I did. Okay. And wrote it basically it is work done divided by SRT, that formula. Okay. Now what is the work done? That's the electrical work done, right? Electrical work done I have to calculate. Electrical work done everybody knows. Like if I know the potential, if I bring a charge, right? It's basically charge into potential. I'm just going to derive that. Okay. For that potential, okay, and for any arbitrary charge, which is like say the ith charge, which is at the center. Clear? Okay. And let us now try to derive the work of charging. Okay. So it's something like, think about it, like there was a ionic atmosphere, right? And centrally there is a charge sitting there. Okay. All I'm asking is that if I charge and discharge this central line, okay, it's an electrical work done. Okay. If it had charge and if it did not have charge, what will be the difference? There will be a difference in electrostatics, and then if I just multiply by the charge, and I should get the work done. Okay. Which means actually, okay, this potential, but everything when you calculate the work done, okay, all I need to know is the potential, because potential is by definition is the work done due to the unit positive test charge, right? If I multiply it by the charge, I'll get the work done. Okay, as simple as that. Now, what is the potential I'm talking about? This is basically the potential of the atmosphere. Now, so far what I was writing, phi I, is the potential due to the charge. Now I am asking what is the potential due to its atmosphere on this charge, because it's a back action, right? Now if I want to calculate it, it is basically the total potential, okay, minus the potential which this guy is creating. Okay. That's basically the central line. Okay. Now let us think about it. What is this phi? Already we wrote like mathematical expression for phi for the ionic atmosphere. It was not exactly 1 by r, it was 1 by r times the e to the power thing. Okay, just let us write it. So I had some constant c, okay, and I had what was that? Basically 1 over r e to the power minus r by r, right? And minus the central one, okay, will always have 1 over r. Why? Because it's a charge. That's what I was telling, right? This is for the charge, this is for the ionic atmosphere. Okay. The difference will be basically the net potential which you are having. Clear? Okay. So there are kind of two potentials here. Okay, one is due to the charge and one is due to its atmosphere, which is also composed of many charges. But those charges were moving and created a continuous distribution in the atmosphere. Clear? Okay. Now if I do it, okay. So what do I want to calculate this atmospheres like effect at basically my central location? Because that is the important thing, okay, where actually the ion is sitting. Which means actually I want to calculate this phi atmosphere at the zero location, because potential is varying. Okay. And again, in our picture in mind, I had a central ion, okay, surrounding it. Again, this central ion is very arbitrary. Okay. I can choose a cation, I can choose an anion, whatever. Okay. But surround the central ion, always I have a diffused cloud. Okay. Everybody is seeing a diffused cloud, something like that. Okay. But everybody, that everybody concept is basically, that's a localized charge, point charge. And all others are actually just kind of giving you an average field. But that average field had an excess charge, that's why there was a charge density. Clear? Okay. So that's what we calculate. Now the question is close to zero, which is basically close to the origin. What will be? I will basically take this expression, take the limit of this expression when basically these are, okay. Let me just write it. Okay. So just let me first write it and then I will just describe it. Okay. Now how do you define a potential? Okay. Like what is a charge like located on, say basically what I am saying here is that I am talking about a difference in a ionic atmosphere, okay, when I am at close to the origin. Now remember what is the definition basically of having a like what is the definition of the work done, okay, electrical work done. So you basically bring an unit positive charge from infinite distance, okay, to this distance, okay, which means what I am trying to say here is that, okay, when, okay, this thing like the divider, okay, will be very large, okay, then only this will be valid. Why? Think about it in a different way, okay, different way of thinking in the sense like if I have a very local atmosphere around an ion, you will have very discrete cations and anions. Okay, but if you want a diffuse cloud description, you have to really make it large. Okay, so in the sense like when this limit or like when this RD is basically much larger, then only I can make this approximation. Which means when x is actually small, which means I can just write it in a very simple way. Clear? So it will be 1 minus x. Okay, I'm just not writing this thing. Okay, you understood, right? And then I'm writing it 1 by r will cancel, okay, and basically be left with something like minus the constant times divided by basically RD. There was 1 by r here, okay. Constant divided by the RD. Okay. So that is basically the atmosphere, how it is basically creating at the center position, okay, at basically r equal to 0 position, okay, close to that. Now the thing is, up to this is very like compacting. What was C was basically this entire constant, okay. Now what is Z into E? Z into E, I said it is a charge, right? So I can just write the constant as minus U, okay, divided by whatever, 4 pi epsilon, okay, into R, something like that. I'm just using a slightly different notation here, okay. Now what will be the work done? Again, work done is basically this potential times the charge, okay. So I'm almost done. So usually you say that, okay, so how do you find the work done? I will always write first the differential electrical work done, okay. And that I will say that it is basically that potential which is the atmosphere is giving, okay, and then suppose I am bringing dq amount of charge. Okay. So I had basically an effective potential, okay, which is the difference between the potential created by the ion and the atmosphere, okay, and that potential we calculated at the origin, which is my center. Now I am saying is that the work done, if I actually add little bit charge to that effective potential, will be basically charge multiplied by the potential. Okay. Now basically I have to integrate it. Okay. And integrate it from where? I know that the work done will be, basically it is work done due to something called charging. I did not have something there, okay, and now I am basically adding charges. Okay. How much charge I can add? That is nothing but Z times C. Okay, so this will be basically the work done. I had 0 charge, and then I am going to a charge, fractional charge, I am incrementing, okay, and I am actually making it up to the cation charge or the anion charge. That will be decided by whether it is a Z plus or Z minus. Clear? That is the differential work done. And then this will be the integrated work done. Okay. Clear? Okay. Now this is basically the work done for one cation. If I just ask you what is the molar thing, I have to of course multiply by the Avogadro number, okay, because this is for one charge. Now as you can see, Na into E, again I will give you an F. Okay. Now what ultimately we will get is what we had, minus Q 4 pi epsilon RT. Just write it here. We'll have minus Q 4 pi epsilon RT dq. That integrated between 0 and A Zi into E. Okay. Now again, what is, so you can see here, right, it will be basically q square, it's a straightforward integration, okay. Now that q square I will again write back as Z into E, okay, and then which means I had here, as you can see, that the q square will have basically Z1 square E square kind of term. Clear? I'm just skipping the step. Okay. So I'll eventually have, and this Na into E I can always write as F, right? So I'll eventually have something like Zi square. Okay. I had F square. Why the F square is coming? It will be basically everything squared, right? Na square E square is basically F square. Okay. And then I'll have 8 pi by 8 because it is q square by 2 integration. Okay, I'll have 8 pi, okay, epsilon, okay, and then I'll have RT. But just 1 minute, just 1 minute, okay, I just did a mistake, sorry. The what done I should have written is like this. Why? Because this is for Na I cannot take square. Basically, it is work done due to one charge, and then that will be squared or whatever, multiplied by the number. I cannot take Na square. Okay. If I do that, think about it. It will be q square. Okay. Q square will be basically Zi square E square. Okay. So Zi square E square by 8 pi epsilon RT. Okay. There is a minus sign, and then there is a Na. That Na square F square I can write as F square, but then I have to divide by Na. Clear? Okay. So I'm kind of done. This is basically the work done. Okay. Now I'm actually done with everything. I have actually work done definition. Okay. In the work done definition, I have an RD. RD also I know. Okay. I'm totally done. All I'm doing right now is to go back to my original definition, okay, and write the numerical thing which we wrote at the very beginning. Okay, so let me also write this thing. W is basically minus Zi square divided by 8 and epsilon RT n. Fine. This is basically electrical work done for 1 mole. Clear? Okay. Fine. Now the final thing, so what I have is basically ln gamma plus minus. Right? That's what we wrote. What we wrote that time, let us go back. We wrote basically it is work done divided by SRT. Right? Now the work done is for cation, is for anion. I have to basically add the total work done. Okay. So I have to basically, it's not actually W by SRT, but a W has two parts, which is basically electrical work done for the cation plus electrical work done for the anion. Because as you can see, what we derive is for I. Electrical work done for I, it is Zi square F square. Right? So I have to add the cation's work done, anion's work done, because there are many I's, there are many central things. We chose a particular ion. Okay. This thing. And then how many atoms are there? Q or P. I think we put P, right? How many anions are there? Q. Divided by S RT. S is basically P plus Q. Done. Okay. Just use the formula, whatever we derive. Okay. So for I have a minus sign here. Okay. And then what I have is P Zi square. Okay. Let us just write it. For E plus, I will write Z plus. Okay, which means Z plus square plus E Z minus square. Okay, divided by, I will have F square, I will just write together. Okay, and then what I have 8 pi epsilon RT into N. Okay, now think about it. In the original expression, which divide, like I am trying to go back actually and try to match it. In the original expression, there was Z plus Z minus modulus. Remember, ionic strength times Z plus Z minus. But here I have actually Z plus square, Z minus square. But I can always play tricks. How? Think about it. This P Z plus square plus P Z minus square. Okay. Just look at it, P Z plus into Z plus, right? And this is P Z minus, sorry, Q Z minus into Z minus. Now for electrical neutrality, we already said P into Z plus has to be basically minus Q into Z minus, right? Has to be. So that thing I can write it as minus Q into Z minus. Z plus, and this guy I'll write into minus P into Z plus, Z minus. So I'll get actually Z minus Z plus thing, and this P and Q is basically S, right? Now basically this S will cancel. Clear? Okay. So what I got is something like, let me just write it here. So I can write it as minus, okay, P plus Q Z minus Z plus, but Z minus Z plus, if I write it in terms of modulus, okay, then this minus sign will be inserted. Okay, because Z minus itself is, if I write it, say sodium sulfate, I shall write minus 2. Okay, so which means this is nothing but S. The negative thing is already included of modulus of Z minus Z plus or Z plus Z minus, whichever we like. Okay. Now let us bring it here. So basically I will have minus S and S, where is the SRT? There was a SRT also. Okay, so I will have basically okay, Z minus Z plus modulus F square divided by 8 pi epsilon RT in A RT. Okay. Clear? Let me just check whether we're done correctly. Z plus Z minus F square 8 pi epsilon tau D, sorry, RT RT. Fantastic. Okay. Now what is RT? RT is this big guy. Okay. Let us actually write it. So minus, okay, is basically 1 over RT. I have to write this thing. Okay, so I have to write it in terms of the reciprocal. Okay, so I have minus z plus z minus modulus. Okay, and what I had is basically epsilon RT, right? Just write it. Epsilon RT. Okay, and what I had twice c f square I into b0, right? Twice c f square I into b0. Okay, that to the power half. That is basically 1 over RT. Okay, and I have rest of the thing, which is basically f square. Okay, and then what I have is 8 pi RT, and then I have epsilon n. Okay, that 1 over RT I already wrote. Okay, so you can just rearrange it. It is basically minus. Let me just write it just a minute. If I write it in terms of cos f okay, so there is f square here, right? I can actually take it out. It will be f cube. Okay, so what I have basically here f cube divided by let me see if we can simplify it a little bit. Just one second. I mean, it's not necessary, but you can just simplify it a little bit. Just one minute. Yeah, so I'm basically trying to just write the final expression with Atkins the way I've written. So these two, okay. Think about it. If I just write 4 pi here, insert 1, 2 here, this becomes 4. So these two and these two gets cancelled. Okay. So I will basically have first write the outside thing 4 pi Na. Okay. Inside thing that 2 I inserted. Okay. So I will have a 2 in the denominator. Okay. I had RT here. Let me insert it. So then I will have R cube T cube. Right. And then I have an epsilon here. Okay. And did I miss an epsilon? Oh, there is an epsilon here. So epsilon also, if I insert, it will be epsilon cube. Okay. R cube T cube, I will have, let me just write the epsilon first. Epsilon cube R cube T cube. Okay. And what I will have in the numerator, I will have basically C tilde. In Atkins, he has written it as rho. The problem is that rho he is using as charge density as well as this. That's why I just wrote it as C tilde. Okay. And then what else I have? F cube already I have taken out. I have B0. Okay. And then I'll just write it. I have I to the power half here. Okay. That base to the power half. I have Z plus Z minus I to the power half. This was basically the A plus A minus I to the power half. Done. So this is the dynamical theory. Okay. Now let me just quickly give you a summary. Okay, how to do it. So now look at the thing here. The thing here is that everything you can calculate. Everything, all the bulk properties. Okay, these are constants. Epsilon, R, T, concentration. Molarity of solvent. B0 is just unitless thing. Z plus Z minus is just the charges. Okay, I is the ion strength. So that actually now you can calculate. Some textbook actually write it as, I mean, I think initially we write it as log gamma plus minus, which means actually there will be a ln 10 factor. Okay, because they wrote it as a log. So this is basically the divided with the limiting law, and it was basically first analytical expression. Okay, for how the ionic how I can actually calculate, okay, the activity for ions. Again, let me actually just give you one quick summary what we did. Okay, first thing first, we said that there was a solute. Okay, how many hours have been? Okay, so first thing first, there was a solute. Okay, 2 hours plus, right? Almost. Yeah. So we said that for the solute, I can use Henry's law. Okay, which is basically looking at that component which is less than xb tends to 0, that limit actually Henry's law is valid. It's an ideal behavior, but not only it is ideal, it is an ideal dilute behavior. So it is for ideal dilute solution. But then it said that how dilute is the dilute? We said that even for ionic solution, even 0.1 mole fraction is too much. Okay, we can only use 10 to the power minus 3 millimolar or less. Okay, where it shows like ideal behavior. So the departure is more for ions. Okay, which means the ionic activities, okay, are much more non-ideal in nature. Clear? Okay. Now the question is why ionic activity? Because now we have to consider the specific interactions between ions. Okay. Then we asked a very simple question. Okay, fine. Then let us actually go back and think about what is the ionic activity. Okay. Now the ionic activity will be something, there is a total activity minus the ideal activity. Okay, and that difference will be basically the non-ideal thing. That non-ideal thing, I can always say that it's a Gibbs free energy difference, and that Gibbs free energy difference has to be connected to the work done. Which work done? Which is a non-PV electrical work done. Clear? Okay. Now, we wanted to calculate the electrical work done. Electrical work done, how do you do? You basically need to know the potential, okay, at some point, okay, and then due to the charge, there is some, due to the charging basically, okay, Atkins has written it as a work done due to charging, as if there was nothing, and then you are putting basically a Jedi charge there, okay, and that work done I have to do. I can think that I have one Jedi here, another Jedi here, there are many of these things, okay. So finally I have to take a sum over the work done due to cations multiplied by the number of cations, work done due to anions multiplied by the number of anions. Fine, that we did actually in the last step here, right? And then this SRT is coming from just the mu thing, okay. But then the question is, if I am actually giving you something in the back thought, because if I just trace back in the reverse way, okay, there was a work done. Now then, how do you calculate the work done? Then I need to know the potential. As simple as that. What potential? Now there is an interesting thing. Now you have to model your system. Okay. It's basically a distribution of charges. Okay, ions are moving around. Now there are two things. Moving around is good because if I consider one ion, other ions are moving so fast, I can think it as a continuous distribution. Then I can actually bring in the concept of density. Okay. So there is an ionic atmosphere which has some density, and there is an ion sitting here. The ion is causing a potential which is purely Coulombic, but the dense thing, okay, which is the ionic atmosphere, which is a continuous charge distribution, that has basically an 1 over r times e to the power minus r type distribution. Okay, but anything like e to the power minus r should have been defined with a characteristic length. Okay, any decay, like it's a decay constant, you can think with respect to a like length decay, right? Now we had to calculate it. Now the interesting thing is that this potential difference ultimately will be multiplied by charges, and that's how we calculate the work done. This was the step which is just before. Now the question is, how did you calculate the potential? Now we used Poisson distribution. Poisson distribution you can use only when there is a continuous distribution of charge, not a discrete distribution. So it said there is a discrete charge, around it there is a continuous distribution, and then we'll sum up for all the discrete charges. That discrete charge, for example, suppose this charge, for a different charge, now it is a part of the continuous distribution. Because when you are sitting over here, this guy is moving actually. That is creating a continuous charge distribution. Okay, so that is the trick they played. Okay, how do you get it? Now you use the Poisson's distribution. Okay, use this idea of spherical symmetry. Okay, so your equation will be only the radial distribution. Okay, radial part of the radial distribution function, and then basically you calculated what is the derivative of the potential. Okay, which will be connected to the charge density. Okay, now once I say this is connected to the charge density, I also had to calculate the charge density. How do you calculate the charge density? I know the bulk number density, but the local charge density will be modified due to the presence of a particular charge which we are looking at, because ultimately we will average over all the charges. Now this local charge, how it is changing? It will basically shift the energy levels up or down depending on whether this is same charge or different charge, which means there is a kind of Boltzmann factoring. Okay, like n by n0. Okay, there is an energy level difference. Okay, how do you calculate it? I can actually calculate the energy, okay, which is due to this charge. How much is the energy, which is basically the potential due to this charge, multiplied by the other charge, Z, whatever we did, okay, and that we cleverly calculated the charge density by saying the charge density is basically the number density times the charges. There was an exponential factor, but we basically truncated it. Why? Because these energy differences will be small compared to the thermal energy cavity. Okay, then we truncated it and we got basically the charge density factor. That charge density is connected, since it's a continuous distribution of charge density, is connected to the potential through Poisson's equation, and since the potential had this characteristic length, expression for RD, d by length. Okay, this is the back thought basically. Probably they thought it in this way. Okay, alright, I'll stop here.